All right, so we're going to do some applications problems now with transversals. Let's see what we can come up with. Installment 133. How old are we? So we're going to first recall one of our old triangle properties, digging in our memory banks. And then we're going to find some missing angles and determining if lines are parallel. Let's see what we got here. So all we're saying here to recall for a triangle property is we should, oops, jumped a slide on you. We should remember that anytime I have three angles in a triangle, no matter what kind of triangle it is, they have to give us a total of 180 degrees. Okay, so that's one that we should all know. So we'll keep that in the back of our minds as we go. So here we go. We've got a survey map of the center of St. John's, and it says it's incomplete. So it is known that Long Hill and Church Hill are parallel for the section of the map shown. Then it says we have to determine all of the angles at the indicated intersections. Okay, so there's lots of letters there that don't have any numbers associated with them. I guess we'd better go after those. So let's see what we got. Well, down here between Gower and Long Hill and Queens Road, I'm seeing a triangle. Okay, so I guess one thing we could say is that x plus y plus 31 should be 180, but we don't know either x nor y, so we can't solve that as it is right yet. Okay, we also know that this angle is 94 degrees, so not quite a right angle, but by straight line properties, b should be equal to 180 minus 94, which I think is about 86 degrees. Okay, so we now know b is 86 degrees. Okay, and it says that Long Hill and Church Hill are parallel to one another, which means that B and W are same side interior angles, which means that they have to be supplementary. So angle W in here has to be equal to 180 degrees minus what we had for B. So that's 180 minus 86, which I think is 94 degrees. And that makes sense because it's corresponding to this one over here. Okay, so now we've got W. All right, I bet we can get angle C out of this as well. Angle C looks like it's 180 degrees supplementary with W, so angle C is going to have to be 180 minus 94 again, and 180 minus 94 is still going to be 86 degrees. Okay, so we're good with that one. Now, to get the rest of them, we have to sort of worry about that other transversal along Gower Street. And to get that other transversal along Gower Street, we're going to have to figure out some stuff inside this triangle. I think maybe this x is going to be a good one to go for because it's vertically opposite that 94. So that makes x relatively simple. It's just going to be 94 degrees. So then angle y we should be able to get because we already said that x plus y plus 31 is 180. So we're going to say that to get angle y, we'll say that x, which was 94, plus y, plus 31 has to be 180 degrees. Okay, so that means 94 and 31 is 125. So we got y plus 125 equals 180. So then y is going to be 180 minus 125, which I believe to be about 55 degrees. Okay, so y is 55 degrees. Okay, so that's a good one. So if y is 55 degrees, I think we can get angle D because angle D is corresponding to angle y. So then angle D should be equal to, running out of space here, let's write it over here. Angle D is corresponding, so that has to equal y, so that's got to be 55 degrees. And then the only one we have left then will be angle Z over here. And D and Z are same side interior, so they're going to be supplementary. So then angle Z is going to be 180 degrees minus angle D. So that's 180 degrees minus, what did we say D was? 55. So that makes that 125 degrees. And that's all of them. Okay. Fun stuff. Who knew there were so many angles on the crazy streets of downtown St. John's? An air traffic control tower is trying to determine if the flight paths of three planes flying at the same height might intersect. That would be bad. A bearing is taken for each of the planes as they cross a line of longitude. Okay. Explain which, if any, of the planes should change course to avoid a collision and explain your decision. Okay, so this would be your line of longitude here, this vertical line. And if that's your line of longitude, and we have these three flight paths, the only way the planes are never going to intersect is if they're parallel lines. So how can we show that lines are parallel? Well, they have to have some of those transversal properties working in their favor. So I can see right now that this angle and this angle are both 90 degrees, or 93 degrees, sorry, which means that they are going to be corresponding angles if we think of our line of longitude as a transversal, which makes this line and this line parallel. This 90-degree angle here, however, that's not a good one. So I guess what we'd have to do is, if we want to make sure we don't have a collision, then the simplest thing to do would just be to get Flight 2 to change its path. So if Flight 2 changed course, at least in the short term, by 3 degrees, then all would be safe. Okay, so why is that going to be the case? This would allow it to make corresponding angles. So if it makes corresponding angles, then all paths are parallel. And that'll do it. So just using our properties of corresponding angles there. So when solving contextual problems using parallel transversals, if solving for angles, apply the properties of the transversal, but if determining whether or not they're parallel, check to see if the properties already hold. And that's it.